Right. Do you know what is Verilog? What is Verilog?
I think it's a language or something.
It is a language, yes.
It's a source file for designing.
Yeah. What type of language is Verilog? Is it used
designing
for
language?
It's what? So sorry, Saud, can you say it again?
Circuit designing language.
Yes, it's called a hardware description language. Okay. So this is the outline of my presentation. I'll talk about hardware description languages. The focus will be, of course, on Verilog. I'll talk about logic simulation versus logic synthesis. I will show you how we can write a module in Verilog. I will show you how we can describe circuits at the gate level. I'll talk about gate delays. I've already talked about gate delays, but we're going to encounter this again in Verilog. I will show you how we can instantiate a module, how we can use the continuous assignment, and how we can write a test bench. So this is my introduction to Verilog. We're going to see more than one lecture about Verilog throughout the semester. So Verilog is a very interesting language. It's called a hardware description language because we use it to describe hardware. That's why it's called a hardware description language. Okay, very simple. Now, we have software programming languages. Okay, we do have we have many software programming languages. Okay, like for example, C, Java, Python, and so on. Now, when you write a program in a software programming language, use a compiler, and the compiler is going to translate the program, which is written in a software programming language, is going to translate it into low-level, let us say, assembly or machine instructions. And these instructions are executed directly by the hardware. Here, we are not doing this. Okay, we are not really using a software programming language. We are using a hardware description language. And the hardware description language, we use it to describe digital circuits and digital systems. That's the purpose of the hardware description language. We can describe the hardware structure, we can describe the gates, for example, or we can describe the behavior. Okay, so we can describe, for example, the circuit in terms of, let us say, logic expressions. We don't describe the gates, we write the expressions. So we can use, okay, this hardware description language to represent logic diagrams, expressions, or even complex circuits. Remember that it's not a software programming language. Okay, so we are not really trying to execute the program on a given computer system. We are trying to describe circuits. So this is a big difference between a hardware description language and a software programming language. So these are two different things. Now, today there are two standard hardware description languages. We have Verilog that we are going to study in this course. And there is also other hardware description languages like VHDL. Okay, VHDL is hardware. Okay, it's slightly harder to learn. Okay, than Verilog. But if you are actually interested, you can also dig deep and find out more about VHDL. Okay, so our focus will be on Verilog. These are not the only two, of course, hardware description languages, but these are the most popular and standard languages for hardware description. Let me introduce Verilog. Now, the word Verilog comes from verifying logic. So you can take here veri and logic. Okay, so Verilog. So back in the 1980s, when circuit designers want to design circuits, complex circuits, they want to verify the correctness of these circuits. To verify them by hand, it's really difficult. Now, for a small circuit, you can verify that. You can you can apply certain inputs, you can see the outputs, you can write the logic expression, you can check that the circuit is providing the correct output for each input. However, when you are dealing with complex circuits, it becomes really difficult to verify this by hand. So for this reason, there was a need, okay, for a language that can verify the logic. This is why they have invented Verilog. So it was invented back in 1984, and it was open to the public in 1990 by Cadence Design Systems, because it was invented, okay, by this company, and it became an IEEE standard in 1995. So it is known as Verilog 95. The language was revised, okay, in 2001 and upgraded. So it became Verilog 2001, and that was revised again in 2005, and it became Verilog 2005. I'm not keeping track actually of all the records when it was revised, but this is the Verilog. So it's a standard, okay, for hardware description. You might also find more information about Verilog on the internet. Okay, it will tell you, okay, when it was revised after 2005. Now, Verilog allows, like other languages, yani for example, if you look at the C programming language, it was revised again and again, and every few years, okay, they revise the language to make sure that, okay, if there were some problems in the language, they will fix it. Sometimes they add new features and so on. Fine. In the case of Verilog, okay, it allows designers to describe hardware at different levels. We can describe anything from a single gate and to a full computer system. That's really very interesting. In fact, we have a variant of the Verilog, which is called System Verilog, if you really would like to describe large systems. Now, Verilog is supported by the majority of electronic design tools. There are really very expensive tools that you can use really to design chips. So these support Verilog. We can use Verilog for logic simulation. We can use it for synthesis. So let me briefly talk about what's the difference between simulation and synthesis. In the case of simulation, we describe a circuit in Verilog, and then we can write a test bench also in Verilog. And the simulator is going to produce timing diagrams, similar to the timing diagram that we have seen, okay, for the AND gate, but we can have timing diagram for a complete circuit. So the logic simulator is going to produce these timing diagrams, and we can use these timing diagrams to verify the logic. We apply input, we can observe the output, and we can see that this is actually output that the correct output that we are expecting, okay, the circuit to produce. So we can predict how the hardware will behave before it is fabricated. That's really the importance of logic simulation. Okay, you would like to verify the logic. You would like to verify that it is correct. So if there are any errors in the design, these can be detected by the simulator. Okay, that's the importance, because it will be difficult to be detected by, to be verified by hand, but the simulator can detect these errors. So this way you can go back to your description and you can modify it so that to eliminate the bugs that exist in the hardware description. The same thing that when you are dealing with software. So when you write software, you can actually run the software, you can debug the software. If there are errors, you can go and modify the software to eliminate these errors that exist in the software. The same thing in the hardware design. So it's not really different. So we can detect this during the simulation and we can correct them. And you can go back to the Verilog description and you can do the modification to the appropriate statements to eliminate these errors that exist in your design, okay? Now, the way that we simulate and we verify a design, we have to write a test bench. So I'm going to show you how we can write a test bench. And the test bench itself is written in Verilog. So you have the Verilog design and you have the test bench. Now that's simulation. What about synthesis? Now, logic synthesis is similar to translating a program. Yani, for example, when you are writing a program in a software programming language, we use a compiler, right? So what's the job of the compiler? The compiler actually is a translator. It translates the program from high level to low level, like assembly or machine instructions. In the case of a hardware description language, there is also a compiler for Verilog. But the job of the compiler is not to generate a program in assembly. The job of the compiler is to produce a circuit. So this is called logic synthesis. So the output of logic synthesis is a digital circuit. That's the output. So what you want is that you would like to have a circuit at the end. Okay. So you can take this digital circuit, okay, So basically, okay, this logic synthesis is going to produce a digital circuit. So it's going to tell you, okay, what are the components and how they are interconnected. So it's going to tell you what are the wires, how do you interconnect these different components. So it's going to produce a net list. So the net list here is a list of components and wires, okay, the interconnections of these different components. This is what we call the net list. Now you can take this, the output of the synthesis, and you can take it and you can let us say, you would like to produce a chip. So you can go to, let us say, someone who can fabricate your circuit, okay, and have it on an integrated circuit. So you can do the fabrication, okay? You can actually take it to, let us say, a computer manufacturer, and you can have your design on a chip. That would be one possibility. Or you can use synthesis to target a field programmable gate array. So the field programmable gate array is a chip. It's called FPGA for short. You can use the FPGA inside the lab. So the meaning of field here, field programmable, it means it can be programmed inside the lab. So you can buy this FPGA chip and you can program it inside the lab. Now, programming here means it's not the same way that you are programming a computer system. Now, programming means that you are configuring the FPGA to implement the digital circuit. So you can implement the digital circuit on the FPGA by doing some kind of configuration, okay, to the FPGA chip. So that will be the importance of synthesis, because you would like to have your circuit on an FPGA chip. Now, the interesting thing about the FPGA is that you can modify it. Okay, you can actually modify and reconfigure the FPGA. So if there are, for example, bugs and errors, you can go and fix them, and then you can do the synthesis again on the same FPGA chip. You can, of course, change this circuit. You can actually modify this circuit. You can actually have other design on the FPGA. So the FPGA chip is actually very useful. You can use it to model different circuits. Now, logic simulation and logic synthesis can be automated. It is automated. People use special software for that. Okay, of course, you cannot actually do it by hand. Okay, it will be very complex to be done by hand. So people use software. This special software is called electronic design automation tools. Right. I'm going to show you how we can write, okay, how we can describe, okay, hardware in Verilog. The way it is done is that we use modules. So any digital circuit can be described in Verilog as modules, as a set of modules. The module here is the design entity in Verilog. The way that you write a module is that you start with the module keyword. So the Verilog itself has a syntax. So we have to use the syntax. The syntax has keywords. So you have to follow the syntax of the language when you are describing the circuit in Verilog. So this is how you start writing so you use the module keyword. This will indicate the beginning of your design. And when you would like to terminate, you say end module. You can have a list of inputs and outputs. So you can actually list them. So we have input and output keywords. You can specify what are the input and output ports. And inside the module, okay, you can describe your circuit by a group of statements. And these statements, you can use them to describe either the gates or the structure or the behavior of the circuit. Right, let me start with a simple example. Okay, this example is a very simple circuit. Notice that we only have 3 gates. We have an AND gate, we have a NOT gate, an inverter, and we have an OR gate. Now, the way that you start describing a circuit in Verilog is that you have to write it as a module. So this is my module keyword. This is the name of the circuit, simple circuit. You give the circuit, the module, a name. And then between parentheses, you write the input and the output ports. So here I have 3 inputs, A, B, C. These are the names of my inputs. So you have to use the input keyword. This is the keyword here. I'm showing it in bold. These are the names of the inputs. So we call them input ports. These are the ports, input ports. We only have two outputs here, X and Y. I have to use the output keyword and followed here by their names, which are X and Y. These are the output ports, okay? Inside this module, notice that the module ends here at end module. This is the end of my module, okay? In between, you can have your description as statements that you write in Verilog. Now, I would like to describe, okay, my circuit using gates. So I only have 3 gates, AND gate, a NOT gate, and an OR gate. So this is my AND gate here. This is my NOT gate, and this is my OR gate. So these are keywords in Verilog, which are used to describe gates. Now notice that the output of this AND gate, for each gate, you can give it a name. So I'm giving a name here, G1, G2, G3. So notice that the AND gate here is named as G1, G2, and G3. These are the names of the AND, the NOT, and the OR gate. Now for any gate, you start by describing the output. So the output of this AND gate is W. So you write W first, and then you write the inputs as A and B. But W is not an input to the circuit. So therefore, what you have to do is that you have to declare W here as a wire. So W is an internal wire inside your circuit. So this is why you have to declare it as a wire. So you always provide here the output, which is W, which is a wire, and then followed by the inputs A and B. These are the inputs A and B for the module, for the circuit. In the case of the NOT gate, the output is Y, the input is C. Finally, for this OR gate, the output here is X. So this is shown here as X, and the inputs are W and Y. So this is W and Y. These are the inputs of the OR gate. So you always write the output before the inputs. Notice that the wire is going to define internal connections inside the circuit. So this is a very simple circuit, which is described at the gate level. This is one way to describe circuits in Verilog. Okay, so do you have any question about this? This is just an example of a module which is in Verilog. So initially, we're going to describe circuits like this at the gate level. In my next lecture, I'm going to show you how we can add delays to these gates. I'm going to show you how we can describe circuit at a higher level using Boolean expressions. So rather than using gates, we can use Boolean expressions and the continuous assignment. So I'll talk about this, inshallah, in my next lecture on Thursday. There is actually more description about this. So input here, output wire, these are keywords. Okay, and NOT, OR, these are also keywords that describe gates. And they can actually be followed by an optional name like G1, G2, and G3. Now, one thing is that the order of these gates is not important because these are not really sequential statements that you are executing in a program. Okay, so this is not an algorithm and you are not describing a sequence of statements. So whether you put the AND before the NOT or the OR on top, it does not really matter. You can write them in any order that you want. The order of the gates is not important. You can show the gates in any order. Verilog is, so the statements which are written inside the module inside Verilog are concurrent. The hardware is parallel. So therefore, you can show all of these gates in any order. Okay, so the meaning of the circuit does not really change if you change the order of the gates. The most important thing is that the wiring. Okay, what are the inputs and what are the outputs, okay, for each gate. Now, as in any language, Verilog has a syntax. So we use keywords. As we have seen in the previous example, we have seen module here, it's a keyword. Input is a keyword. Output is a keyword. Same thing about wire and OR. And not OR and module here. All of these are keywords. So these keywords are reserved in the language. You cannot use keywords as the names of identifiers. On the other hand, we have identifiers. These are user-defined names. You can define your own name for a module. You can define names for the input ports, for the output ports. You can define names for gates, for wires, and so on. So as we have seen in the previous slide, simple circuit is an identifier. Okay, A, B, C, these are identifiers, names of inputs, names of outputs, the name of a wire, names of gates, and so on. So these are called identifiers. Now you have to be very careful about identifiers. Verilog is case sensitive. It means that if you write the name in capital or lowercase letters, it's different. So capital A is not the same as lowercase a. So this is known as case sensitivity. Okay, it's like many software programming languages, the identifiers are case sensitive. You can also write comments. There are two types of comments that you can use in Verilog. You have the single line comment, which starts with // and terminates at the end of the line. And we have the multi-line comment, which is surrounded by /* and // as in the C programming language. You can use white space freely. Okay, you can have the space character, the tab, the new line. Okay, so you can use them freely in your hardware description. Finally, we have operators, and Verilog has a rich set of operators that we are going to study later that you can use in Boolean expressions. For example, we have the NOT operator, we have the AND operator, we have the OR operator, which is written as a vertical bar. There is also XOR. You can use also for arithmetic plus, which means addition, minus, which means subtraction. So all of these are also operators that exist in the Verilog language. So as we have seen in the previous example is that we have basic gates. So these are defined as keywords in the Verilog language. So there is a list of gates. For example, you can have AND, NAND, OR, NOR, XOR, exclusive NOR, NOT. There is also buffer. There are also other gates other than these, but these are the main ones. Okay. So we define them as these are defined in the Verilog hardware description language as keywords. I'm showing them in bold, okay, to indicate that these are okay, they are actually keywords in the in VHDL. You can write an optional name after the gate. Yani, for example, you can say AND, you can give it a name like G1. And then you write the output first, followed by the list of inputs. So here, for example, X is the output, A and B are the inputs. So you always write the output followed by the list of inputs in the case of gates. Okay, so you write the name first, between parentheses, you write the output, and then you can have multiple inputs. You can have a gate with 2 inputs, with 3 inputs, with 4 inputs. So Verilog allows you to have multiple inputs, not just limited to 2, but you can also have more than 2 inputs for a gate. Except in the case of the NOT gate and the buffer, these have only 1 input. So if you have a NOT gate or you have a buffer, okay, so the NOT gate is the inverter, it only has 1 input. Now let us take a look at this example about how we can model a half adder. Now a half adder is a very simple circuit. What it does, it adds only 2 bits, A and B. So we're only adding 2 bits. This is a building block, an essential building block when we would like to design arithmetic circuits. I will talk about arithmetic circuits in great detail later. So, so it's a very simple circuit. Okay, so we have only 2 inputs, A and B, and we would like to add them. And when we add them, we get 2 outputs, a sum bit and a carry out. That's the half adder. So we can draw a truth table for the half adder. These are my inputs. We have 2 outputs, C out, and we have sum. These are the outputs. Now, because we have 2 inputs, there are 4 entries in the truth table. Notice that when the input is 1, 1, so 1 plus 1 will give me 2. But the way that you represent 2 in binary, it will be 0 and the carry. It will be 1, 0 in binary. So the sum will be equal to 0. And the carry will be equal to 1. That's when you get a carry, when you have the two inputs, both inputs are equal to 1 and 1. So from this truth table, we can see that we have two outputs. We have C out and we have sum. Now, if you look at C out, it's very simple. You get a 1 when A is equal to 1 and B is equal to 1. So we can directly write the equation for C out. C out is A and B. You see, this is very easy. In the case of sum, this is the column for sum. We get a 1 when you have one of the inputs is equal to 1, but not both. So therefore, sum is A XOR B. So this is my equation for sum. So if the input is 0, 1, or the input is 1, 0, this is when you get the sum is equal to 1. If both inputs are 1 and 1, you get the sum equal to 0, and there is a carry. So the sum will be equal to 0 if A and B are both 1 and 1. Now, once we have these equations, what we can do is that we can easily model. We have the circuit diagram. So this is the sum, which is A XOR B. So I need XOR gate. And this is C out, which is just A and B. So we need an AND gate. And we can model this very easily in Verilog. So this is my module. I'm calling it half adder. That's the name of my module. These are the inputs A, B. These are the outputs C out and sum. Notice that input and output here are defined inside the module. Now, this is the old Verilog syntax. It's called Verilog 95 syntax. So back in 1995, they used to define the inputs and the outputs inside the module. But today, we write them inside the parentheses. So we put here the input before A, B, and we put the output before C out and sum. So we write them directly in the list of input and output ports. So we don't write them inside the module. This is the new syntax of Verilog. So the syntax of Verilog changed over time. We have two gates. I have the AND gate, I have the XOR gate. So the output of the AND gate is C out. The inputs are A, B. The output of the XOR gate is sum, and the inputs are also A and B. So this is how we model a half adder in Verilog. This is very simple. Now, when we get the carry out, okay, and I would like to add, let us say, two numbers in binary, this carry out is propagated. It becomes the carry in of the next bit. So when you are adding, let us say, multiple bits, suppose I would like to add 8 bits plus 8 bits, as we had seen at the beginning of the semester, the carry out is propagated, okay, to become the carry in, okay, for the next bit. So therefore, you will end up adding 3 bits vertically inside a number. So for this reason, we need a full adder. So the full adder is an adder which can add 3 bits. Okay, so it's a building block which is used in, let us say, in a large adder. So it is capable of adding 3 bits A, B, C. So we are adding here A, B, C. So we are adding A plus B, and the C here can be the input carry, which is the output carry from the previous bit. So you might actually have to add A plus B plus some input carry. So that's the C here, okay, which is a carry which is propagated from one bit to another. Right, if I would like to add 3 bits, we have to draw a truth table. And to draw this truth table, we have to list all the entries inside this truth table. So if we have the correct truth table, then we can obtain the equations. Once we have the equations, we can draw the circuit diagram, and we can easily model this in Verilog. That's basically it. So we have 8 entries in this truth table. You can see that we start here at 0, 0, 0, and we end here at 1, 1, 1. We have 2 outputs, like in the case of the half adder. We also have 2 outputs in the case of the full adder. We have a sum bit, and we have a carry out. So we take it entry by entry. So we add 0 plus 0 plus 0. This will give me the sum equal to 0, and there is no carry out. So this is here my first entry. Sum equal to 0, C out equal to 0. And then you go down. For example, when you reach the last entry here, 1 plus 1 plus 1, this will give me 3. But 3 in binary will be 1, 1. So therefore, the sum will be 1, and the C out will also be equal to 1. Okay. Remember that the carry is 2. Okay, so basically the carry has a weight of 2 in binary. In decimal, the carry will be 10, but in binary, the carry is only 2. Right, so you can see that this is the truth table of the full adder. For example, let us take another entry. Let us say I would like to add 0 plus 1 plus 1, 0, 1, 1. So 0 plus 1 plus 1 is 2. So you can see that the sum is equal to 0 and the carry is equal to 1. Okay, so this is how we define this truth table for the full adder. Now, once we have the truth table, what I need the equations. I need the equations for sum, and I need the equation for cout. If you look at if you would like to determine the equation for sum, just look at this column here for sum. If we look at this column, okay, for sum, you can see that the sum will be equal to 1. So it's equal to 1 here, 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 and here. So we have 4 entries in which the sum is equal to 1. Now, sum is equal to 1. If you look at the inputs here, when you have the total number of ones, so here we have a single 1 in the inputs. Here I have a single 1. Here I have single 1. And here at the bottom, we have 3 ones. Let me clean up this slide one more time. Okay, I need to erase all the ink. So you can see that sum is equal to 1. There are 4 cases. So here we have ABC equal to 0, 0, 1. Here I have sum is also equal to 1. So ABC will be 0, 1, 0. So also we have a single 1 in the input. Here I have 1, 0, 0. That's also will give you 1. And here I have 1, 1, 1. This will also give me 1. So if you look at the number of ones in the inputs, okay, the total number of ones in the input is odd. And either we have a single 1 or we have 3 ones. So that's an odd number of ones. So the sum function here, the sum output is an odd function. So we call it an odd function. Already I talked about odd function before. So this is an odd function. So we get a 1 when the total number of ones in the input is odd. That's why it's called an odd function. So if you count the number of ones in the input, it is odd. That's the meaning of odd function. Now we know that odd function can be expressed using the XOR gate. Of course, we can look at these as minterms, and I can write the expression as a sum of minterms as we have done before, but we'll not do this, okay? Because it's a lot easier. If I would like to write it as a sum of minterms, it is going to be a long expression. So it's a lot easier to use the XOR gate. So this is here the advantage of the XOR gate is that we can use it in full adders. So the sum here, okay, can be written as A XOR B XOR C. So this is my equation for sum. And the reason why we are using the XOR is that because we have an odd function. So A XOR B XOR C will give me 1 if the total number of ones in ABC is odd. That's my odd function. Right, how about cout? Now that will be the output carry. You can see we have 1 here, here I have 1, here I have 1, and here I have 1. Okay. So if you look at the cout, the output carry, you should have 2 or 3 ones in the input. In order to get an output carry in a full adder, the number of ones in the input should be either 2 or 3. And if you have a single 1, then you will not get a carry. So you have to have at least 2 ones in the input to get an output carry. So if I would like to get the equation, okay, for the output carry, let me erase this and this here. Now for the last 2 ones here, notice that A and B are both 1 and 1. Now notice that how I'm reasoning about the equation here. Okay, so later I'm going to show you using the Carnot map technique how we can get minimal equations for these expressions, but I'll talk about this inshallah next week. But in this lecture, I would like to show to you how we can obtain the cout. We can reason about the equation for cout. So if A and B are both 1 and 1, I'm going to get a 1 in the output. I'm going to get 1 in C out. So C out will be equal to 1 if you have A equal to 1 and B equal to 1, regardless of C. So it is sufficient to have two inputs are equal to a 1 to get the carry out equal to 1. So this is A and B in my equation. So if A equal to 1 and B equal to 1, then this will give me C out is equal to 1. So these are these two cases. Now the other two cases, okay, are here, here, and here. Now here you can see that we have either A or B equal to 1, but not both. So this is A XOR B. So A XOR B is equal to 1 if either A equal to B. So if either A equal to 1 or B equal to 1, but not both. But then you need a second one. So this must be C. So we write it and C. Okay. So this is my equation for C out. So we have A and B, or we have A XOR B between parentheses and C. That's how we get the equation for C out. So this will produce all the ones for C out. Now, once we have these equations, all what we have to do is we have to draw the circuit diagram. Now that will be easy. And then after that, we can model this in Verilog. Now notice that A XOR B is used in sum and in C out. So I can use the same XOR gate, okay, for the sum and for the C out, and this way you can reduce the logic. Now this is the circuit diagram, okay, for the full adder. Notice the inputs here are A, B, C. We have two outputs. We have sum, we have C out. In the case of sum, we have A XOR B. That's A XOR B. This is the first XOR gate. XOR C. This will give me sum. So I need two XOR gates. In the case of C out, let us go back to the equation. This is the equation here for C out. So it's A and B, or I have an OR here, an OR gate. I have A XOR B and C. So A and B, this is A and B. That's my AND gate. The output will be called W1. That's wire 1. And here I have A XOR B. That will be output will be called W2. Ended with C. That's my AND gate. The output will be equal to W3. This will be wire 3. And then finally, I need an OR gate. So this will give me C out. So in total, we have 5 gates. We have 2 XOR gates, we have 2 AND gates, and we have 1 OR gate. I can easily model this in Verilog because we have the gates. So this is my module, which is called full adder. I have 3 inputs A, B, C, and I have 2 outputs C out and sum. So notice the syntax. Now the input and the output keywords appear in the port list. Okay, so I don't really define them inside the module. I define them between parentheses. I have to declare 3 wires. So this is my wire keyword because I need them in the gates. So I have 3 wires, W1, W2, W3. I have here 2 AND gates. So the first AND gate will be this one here. This is the first AND gate. The inputs are A, B, the output is W1. The second AND gate is here. Okay, so you have W2, C, the output is W3. I have 2 XOR gates, and I have an OR gate. So basically what you have to do is that you have to wire them. And the first XOR gate, if you look at the first XOR gate, which is shown here, this is my first XOR gate, this one here. Okay, the inputs are A, B, the output is W2. So you just have to track things. I'm just scratching a lot of things on the screen here. Let me clean up things. So this is my first XOR gate here, right? You can see the output is W2 and the inputs are A and B. So that's W2, this is AB. This is basically how you write the output first and then the inputs. So once you have described, okay, the full adder, okay, using the gates, khalas, we are done. Okay, so you can show all of these 5 gates inside the module, and this is a gate level description. It's a gate level description of the full adder. Notice that the gates can appear in any order. Yani even if you write the XOR before the AND, or you write the OR even first, it does at the top. It does not really matter in what order these gates appear. Now, because the gates themselves are, the hardware itself is parallel, and the gates are going to work independently of one another. So basically, the gates are sensitive to their input. And once there's a change in the input, the output is going to change. So for this reason, the gates can appear in any order inside the module. Now, one thing you can do in Verilog is that you can associate a delay. You can have a delay for each gate. Okay, this is good for simulation purposes. Sometimes we know what are the gates. For example, for a given technology, information is given to us about the delays of gates. So maybe I would like to simulate not only the functionality of the circuit, but also I would like to take into account the delays inside the gates and inside the circuit. So this will be good. So Verilog allows us to associate a delay with each gate in our description. So let us go back to the example about half adder. We only had two gates, AND gate and XOR gate. Okay, that was the half adder module. Now, if you want, you can have, for example, the delay of the AND gate is shown here, which is #2. It means 2 time units. And the delay of the XOR gate is shown here, which is #3. So we use the hash symbol to specify the delay of a gate. So this is very useful, okay, when you would like to simulate circuits and you would like to see the delay. Now, the time unit can be specified with a time scale. So Verilog, okay, has a directive which is called time scale. So you write time scale here. Notice that you write a small backward quotation, okay, before time scale. This is important. Okay, so you have to use this back quote before time scale. This is called the directive. And then you write two things. You write the time unit. So here I'm using the time unit, which is 1 nanosecond. So this #2 will be 2 nanoseconds, and the #3 will be 3 nanoseconds. You can also specify the precision. So the precision here is given as 100 picoseconds. So that's the smallest unit which is used by the simulator. Now we know that picosecond is smaller than a nanosecond. So nanosecond is 1/1 billion of a second, and pico is 1/1 trillion of a second. So if I would like to write it here, it's shown here. The nanosecond is 10 to the power -9 seconds. That's the nano. And the picosecond is 10 to the power -12 seconds. So in fact, when you look here at 100 picoseconds, 100 picoseconds is less than a nanosecond, 0.1 nanoseconds. Because 1,000 picoseconds is equal to 1 nanosecond. So this is the time scale. So you can write this directive, okay, before the module. That's one way of doing it. And sometimes you can also specify it inside the simulator as an option. Yani you can actually indicate to the simulator, please use this time scale. You don't write it as a directive, but you specify it inside the simulator. So you can do it either way. Okay, either you can provide it as an option to the simulator, or you can write it as a directive before the module. Writing it as a directive is actually becomes very clear. Okay, so now these delays, the #2 and the #3, will use the time unit that we have specified. So therefore, we are dealing here with 2 nanoseconds and 3 nanoseconds. So we are giving these two different delays for the AND and for the XOR. Now notice the delay for the XOR is slightly higher than the delay for the AND. Why? Because the XOR itself is a more complex gate than the AND. So we expect the delay in the XOR to be higher than the delay in the AND gate. Again, these delays, we can obtain them depending on the technology. Maybe these actually are slow gates. This is old technology. Maybe today's technology, the AND and the XOR will have much smaller delays, maybe in picoseconds, not in nanoseconds. But this is just an example to show to you how you can have a delay, okay, for these gates. This is a full adder module with gate delay. The same full adder module that we have seen in the previous slide. I just added gate delays. So notice that the AND here has a delay of 2 nanoseconds. The same thing here. The OR has a delay of 2. The XOR has a delay of 3 nanoseconds. So this is good if you would like to simulate the delays inside the gates, and this will give you also the delay in the circuit. Right. So what we have seen so far is that we have seen a one way to describe circuits in Verilog, which is a gate level description. Now, gate level description is tedious. If you have, for example, a circuit that has hundreds or thousands of gates, well, I'm not going to describe it the way it was described in the previous slides. Now, having, let us say, few gates, maybe 5, 10 gates, that's okay. But if you have really a large circuit and you would like to describe, okay, the circuit in Verilog, we don't really use a gate level description, even though we can, but we don't, okay? So what is a better way of describing a circuit in Verilog? Well, we can describe the functionality of the circuit or the behavior of the circuit. Now, that will be a lot better than describing it at the gate level. So the way to do it is to use continuous assignment. Continuous assignment is a powerful statement that exists in the Verilog description, hardware description language. So the way that you write it, the syntax is that you write assign. So this is a keyword followed by a name. For example, this can be the name of an output port, or it could be a wire, for example, that you have declared inside the module. And then you write the assignment operator, and then you write an expression, okay? And of course, you terminate this with the semicolon. So this is the syntax. This is how you write continuous assignments in Verilog. So these are examples here. For example, you can write assign. You have to always start with the assign keyword. Now, this is called continuous assignment. I'll mention why it's called continuous, but let us focus first on the way that we write. So for example, here X, okay, is my name. Okay, as I said, it can be like an output port, or it could be a wire, for example. So you can only assign to wires or to outputs. And then you write here the assignment operator, and this is my expression. Now, within the expression, you can write, let's say, you can write Boolean expressions. You can write the AND operator. So this is the AND symbol. This is also AND. This is NOT. This is OR. So you can actually use all of these operators. Okay, so don't use the plus for OR, because plus means addition in Verilog. So if you want to say OR, use the vertical bar. So make sure to write the operator properly when you are writing a Boolean expression in Verilog. Notice the AND operator. So we have operators here. This is NOT. This is AND. It is shown here. This is NOT. This is AND. This is OR. This is XOR. You can also have a symbol for XOR. Okay, you can also use parentheses for grouping and to give precedence. Okay, so the parentheses will have the highest precedence when you have like complex expressions. You can use also parentheses. And for example, this will be A or B between parentheses and not C. This will be the way that we describe it in Boolean algebra, but in Verilog, you have to use the correct syntax. This is not A or B or C, so this will be a NOR gate, a 3-input NOR gate. This will be A XOR B XOR C. So notice the XOR here. Okay, so we're using 2 XOR gates. So you can really describe really long expressions, complex expressions, without having to describe them gate by gate. You can just write the expression. So this is very useful, okay, in Verilog, and it makes the task of the one who's describing, making the description, okay, so writing the description in Verilog becomes a lot easier when we use continuous assignment. Now, the reason why it's called continuous assignment is that this assignment is not done once. It's not like in a software programming language. We are not doing the assigning the values to X once and that's it. Okay, so we don't evaluate the expression once. Now, this assignment is continuous, okay, which means that anytime there is a change in the values that appear on the right-hand side of the assignment operator inside the expression, we have to go and re-evaluate the expression. And if there is a change, we assign a new value to the name that appears to the left-hand side of the assignment operator. Okay, so let me say this one more time. So the assignment is continuous. And therefore, if there is any name that appears, any, let us say, variable that appears in the expression on the right-hand side of the assignment operator, anytime there's a change, we have to go and re-evaluate. And if there's a change in the input, then we have to go and re-evaluate the expression and reassign the new value of the expression to the name that appears on the left-hand side of the assignment operator. So that's the meaning of continuous assignment. Now you can have multiple continuous assignments inside a module. And again, these assignments are parallel. These continuous assignments are parallel. They are not related to one another. And therefore, their order can appear in any order inside the module, like gates. Fire. We can also add a delay to continuous assignment. That's also provided in Verilog. So this is optional. So you might have a continuous assignment with or without delay. So the way that you write a delay, this is the syntax. You write it like this, hash delay. So you write a hash and then the delay, and you can specify the delay of the assignment. Now here what you have to do is that you have to estimate this delay and put this number, okay, because this delay is for the whole expression. Okay, it's the propagation delay. It's not a delay of a single gate. No, it's a delay for the entire expression that appears on the right-hand side of the assignment operator. And for example, if I would like to describe a full adder, I can describe sum with one expression, and I can describe cout with another expression. So I only need two continuous assignments, one for the sum output and one for cout. So here sum will be A XOR B XOR C. That's the expression for sum. And this is my expression for cout. It's A and B, or A XOR B and C. Okay. So what we need to do is that we need to assign. Okay, we need to assign a delay for sum, and I need to assign a delay for cout. Now, in the case of sum, if the delay of the XOR gate, which is shown here as XOR operator, suppose that the delay of each XOR is 3 nanoseconds, and we have 2 XOR gates. So we add 3 plus 3, this will give me 6 nanoseconds. So therefore, the delay of sum will be 6 nanoseconds. So again, we go by the maximum delay. Okay, so that's the propagation delay. Okay, from the input to the output. Now, in the case of cout, notice that I have an AND gate. So suppose the delay in the AND gate is 2 nanoseconds. First, I have this XOR gate. So this is 3 nanoseconds. Here I have plus 2, because we have the delay of the AND. Here I have an OR gate, which is another plus 2. So we add 2 plus 3 plus 2. This will give me 7 nanoseconds. So we assumed in the previous description, if we go back to this description, that the delay of the AND is 2, the delay of the OR is 2, and the delay of the XOR is 3. So we're using the same delays here, but notice that we are associating this delay with the whole expression. Okay, and again, we go along the critical path, as I talked about it in a previous lecture. So we go along the longest delay from the input to the output. So that's my delay for cout. It is 7. The delay for sum, it's 6. So you might actually have different outputs with different delays. That's okay. You can describe this in Verilog. Notice that the order of the assigned statements does not really matter. You can say assign cout before assign sum. So they can appear in any order. These are two independent continuous assigned statements. And they are both continuous, okay, because they can change their values continuously. Okay, so when you are simulating this module, if you change the inputs, the outputs are going to change, okay, continuously. So for this reason, we say that these are continuous assignment, and we say that, okay, each assigned statement, it is sensitive to its inputs. Yani, for example, in the case of sum, if you look at sum, the inputs appear on the right-hand side. We have A, B, C. So any change in ABC, so we say that sum is sensitive to the inputs ABC. The same thing for Cout. The inputs are ABC, so it is sensitive to whatever are the inputs that appear on the right-hand side of the assignment operator. So any change in the values of the input ports ABC, we have to re-evaluate the expression to produce the new sum or Cout output. Right. Once we have done all of this, what is the last step? Is to write a test bench. So what is a test bench? The test bench is necessary because we would like to apply inputs to a given circuit, to a given module, and would like to use the simulator to generate the output so that we can verify the correctness of the circuit. So the purpose of the test bench is to verify the correctness. That's the purpose of the test bench. Now, the way that we write a test bench, we write it also as a module in Verilog, but we write it as a module with no ports. So it has 0 ports. So what we need to do is that inside the test bench, we instantiate the module, and then we provide the inputs, and then we observe the output. Now, the test bench itself can be complex, depending, of course, on the complexity of the design that we are trying to test and verify. So it could be lengthy, depending, of course, on how complex is our design. I'm going to show you a simple test bench. So suppose I would like to test my full adder. Okay. You write a module, you give it a name. For example, I'm calling it here test full adder. That's the name of my test bench. You can call it full adder test bench or whatever you would like to call it. This is just an identifier name. Notice that we don't write any input or output ports. So there are no inputs, there are no outputs for the test bench. Now, in order to test the full adder, I have to instantiate it inside the module. This is called module instantiation. Okay, this is also another concept that we need to understand very clearly in Verilog. So inside this module, this test bench, what I really need to do is that I need to create an instance of full adder. So this is my full adder. This is my full adder. This is the name of the module. I need to test the full adder. So I'm going to write the name of the module followed by the name of the instance. So here, FA here, it is just a name for the instance. So we have 2 names. We have the name of the module. We have the name of the instance of this module. Now, why do we write it like this? Is that you can have multiple instances. You can actually have, let us say, more than one full adder. You can instantiate multiple full adders. So each instance will have a different name. So the name of the module can be the same, but you can create multiple instances of the same module. And then you can provide the inputs, and then you can provide the outputs exactly in the same order they are defined inside the full adder module. So I need 3 inputs ABC. I need 2 outputs Cout and sum. You don't really have to call them ABC or Cout and sum. You can give them XYZ, for example. It does not really matter. Okay, when you instantiate the module, your inputs and outputs can be different than the names that exist in the module that you have defined. But in this example, just for simplicity, I'm just using the same names. Now, ABC here are my inputs, and these inputs are going to vary inside the test bench. So therefore, we have to declare them as variables. So we use the register type. So here, register, it means variable. In Verilog, register means variable. So ABC here must be of type register. It means that ABC are variables. Now they have to be variables because we are going to change their values inside the test bench. Whereas Cout and sum, okay, these are wires because these are the outputs of the circuit. So we declare them as wires. Now, in order to provide values, okay, assign values to these inputs, we have to write an initial block. So notice that this is my initial block. It will start at the initial keyword, and then you surround it by begin and end. And inside, you can write a number of procedural assignment statements. So the body of the initial, so this is used actually mainly for initializations, but we are using it here to provide test cases, okay, inputs to the full adders. So initially, okay, when the simulator starts at t equal to 0, I would like to initialize A, B, C. So A will be 0, B will be 0, and C will be equal to 0. Okay, that's initially at t equal to 0. So when the simulator starts, it's going to start in this initial block. It's going to start executing the initial block statement by statement. So this will be at t equal to 0. Then after 20 time units, for example, the time unit can be nanoseconds. So after 20 here, so you can write hash 20 before this statement. It indicates that this statement is delayed in the simulator by 20 nanoseconds. So we're going to make A equal to 1 and B equal to 1. And then after another 20, we're going to change the value of A and B again to 0, 0, and make C is equal to 1. So now at t, so you see that this hash 20 here is delayed with respect to this hash 20. So therefore, this will be at t equal to 40. So at t equal to 20, we make A equal to 1, B equal to 1. And then after another 20, which means at t equal to 40 time units, we're going to make A equal to 0, B equal to 0, and C is equal to 1, and so on. So every 20 time units, we change the values of the inputs. And then finally here, okay, at t equal to 80 time units, we finish the simulation. So this is an example of a simple test bench. I'm going to show you, okay, I'm going to take a few extra minutes, okay, to show you a demo. Okay, I'm going to show you a demo in the last maybe 10 minutes or 15 minutes. We'll see. Try to make it quickly. Okay, so notice that here there is a difference between register and wire. Okay, this is explained here in this slide. So wire is called a net data type. So net here means wires. Okay, so like wires that we have in real circuits. On the other hand, the type register, okay, it means is a variable data type. So Verilog distinguishes between register and variable, register and wire. So register means variable, and wire it is just like wires that we have in circuits. The initial statement, we have seen it in the case of the test bench. Okay, so the body is called procedural. So when you write an initial block, the body of this block is procedural, and the statements which are written are called procedural statements. So what we have seen in the test bench is that we wrote procedural assignment, and these are written like this: hash delay, variable, assignment operator, expression. Now we wrote these inside the body. So notice that here we say A becomes 1, B becomes 1. Notice the delay here, hash 20. Now these A becomes 1, B becomes 1. These are procedural assignments. These are not continuous. And A and B must be variables. So we're assigning A becomes 1 and B becomes 1, like in any software programming language. Now they can vary during the simulation time, because we would like to change the inputs. So this is why they have to be variables, and we can vary them. And the statements which are written inside the initial block, they are executed sequentially, exactly the same way that we execute statements which are written in a software programming language. That's the initial statement, and then we can run the simulator. So I'm going to stop here, okay, and I'm going to show you a demo. So what I did is that I used ModelSim on my computer to generate these waveforms. But let me show you how you can use a simulator online. So I'm going to bring here my browser. Okay, and I'm going to use EDA Playground. Okay, so what we have to do is that we have to go. So I'm logged out because this is really okay. So what you have to do first is that you have to create an account. You have to log in. And then once you log in, you can use your account. For example, here I'm using my account at KFUPM. You can actually have your own password, of course, and then you can log in. Now, when you log in, notice that you will have here two windows. One is for the test bench and one is for the design. So SV here means system Verilog, but you can use it to write Verilog, or you can use system Verilog. In this course, I'm going to only talk about Verilog. So what you have to do is that you have to write your design modules. You can have one or more modules here inside design. And under test bench, you write your module, which is the test bench for testing the modules under design. Okay, so that's how you write the code. Now, I already have written a lot of examples, so I'm going to show you some of them. So let me here, after logging in, you can go to your playgrounds, and this will show you, for example, the modules that you have saved. So I'm going to choose here full adder. By the way, if you go to the website for this course, I have links I made some of these modules public so that you can actually view them, you can try them. This is made public. So notice that here I'm putting actually public. Anyone with the link can view. So I have links. The link is shown here on top. Notice that what is shown here on top, this is the link. Okay, so you can share the link, okay, especially when you have an assignment and you would like to submit this assignment, you have to show us your link. So you put it inside the document, right? So this is a copy of the full adder that we have seen in the presentation. And this is here, okay, you can, okay, so you can, you need probably a large screen to see this. So this is my test bench. It is just actually a copy of the test bench that we have seen. Now, what you have to do is that you have to go under tools and simulators. Now you have to select, okay, which tool or which simulator. I'm going to use this simulator here, which is a free. This is the Icarus Verilog 0.10. Okay, so I'm going to use this. I'm going to click here under Open EP Wave after Run. Okay, so therefore you can actually see the waveforms. So what we can do is that we can take this and we can simulate it. By the way, I have also another one. If I go to Playground and I go to, this is another full adder, but it is with continuous assignment. So notice that how I'm using assign. Okay, this is for continuous assignment. This is sum, this is cout. I'm describing them with Boolean expressions. This here is the XOR. I'm using AND, or I'm using here the, so you can use these operators that exist inside Verilog. So what you have to do is that you have to select your simulator. You can open. Notice that in the case of the test bench, you have to write two extra statements. So one is called dump file. Okay, for example, you can dump, you can use this name here, testfulladder.vcd, and then dump vars, okay, to see the variables that exist inside this test bench, because you would like to view them. And this FA here is the name of this instance of this full adder. And this one here indicates the level. So you'd like to have it at level 1. So there are actually tutorials actually for the EDA playground that you can actually watch. I also have many examples that I placed. So what you have to do is that if you make changes, you can actually press here on save. You can copy to create additional copies if you want. And then you can run. So when you run, the compiler is going to translate this code and is going to open a new, this is basically came in another window. That's, this is the EP waveform viewer. So you can view the waveforms, and this shows the waveforms. This will show A, B, C, cout, and sum. And notice that how we are initializing A, B, C at equal to 0 to become 0, 0, 0. But because the cout and the sum are delayed by 7 nanoseconds, initially cout, the output cout, and the sum are not defined except after 6 and 7 nanoseconds. So the red here indicates that the output is not defined. So we say undefined, it means that we don't know if it is 0 or 1. So this is why it is shown in red. But after a delay, cout is delayed by 7 nanoseconds. So you can actually look here, you can see this is 7. Okay. Now, after that, you can see that how it is delayed. Now, at t is equal to 20, notice that how we are changing A, B, C. Now, this change in the output, for example, when you have A, B, C are equal to 1, 1, 0, the sum will be 0, but the C out becomes 1. But C out is delayed. So therefore, the change in C out will not really happen instantaneously, but it's going to be delayed. So for this reason, you can see that how it's delayed by 7 nanoseconds because we wrote so in the description. So you can see the waveforms, and you can verify the correctness of these waveforms when you are using the EDA playground. So in this course, we are going to use the EDA playground. It's really very easy to use. As I said, there are tutorials. You can keep track of time here. For example, this will be 27 nanoseconds. Notice that here I used the time scale 1 nanosecond, 1 nanosecond. So everything is nanoseconds. You can change the time scale. You can use picoseconds if you want. So all of these delays are in nanoseconds. So that's one description. If I would like to use my other description, for example, if I go back here to my playground and use the gate level description. Okay, so that's my gate level description for my design. This is the same test bench, but I use a different design here, and I run it. Okay, so we are going to get different waveforms here. I'm going to get C out some, but this also will show me W1, W2, W3. These are the internal wires that exist in the inside my design, okay, for the gate level description. So look at these waveforms and see how the delays are, how the waveforms are produced according to these delays. Now, this is gate level description. You will find actually some differences between the gate level description and between the continuous assignment. Okay, so this is very interesting. You can actually view it, you can look at these waveforms, and you need to understand these waveforms. Of course, if there is zero delay, these actually changes will appear instantaneously. So here, for example, when A is equal to 1 and B is equal to 1, you will get W2 is equal to 1. And then you get C out is equal to 1, but this will be delayed. So W2 is A and B. Okay, so you can go back to the description here that we are using an AND gate here, for example, for W1. Here we are using XOR gate, and so on. So basically, you are using this model, not the continuous assignment model. So it's interesting actually to look at these waveforms and understand them. Okay, this is basically called simulation. You would like to simulate your circuit and you would like to observe the output. So the test bench provides the test cases, the inputs, and then you can use the EP wave to watch the waveforms. Right, so that's it. This is my tutorial about Verilog. I recorded this video, so I'm going to upload it on MS Teams so that you can watch it during the week. And next week, inshallah, I'm going to post the first Verilog assignment. Thank you for watching. I will see you, inshallah, next week.